It's very exciting to be here and present you our work, Echo Plus, an FPGA-based collective engine for distributed applications. And this is a joint work between ETH Systems Group and AMD Research. So in the past years, we have seen a large deployment of FPGAs in the data center, and they are used as accelerators and also as useful tools to support specialized infrastructure and dynamic workload. And also, as mentioned earlier in the morning in the keynote talk, the specialization can also be a very useful technique to bring more efficient power consumption in the data center. And one prominent example of utilizing FPGAs in the data center is the Microsoft Cartable and Brainwave project, where they offload the network function visualization, storage optimization into the hardware, and also they distribute neural network across a fleet of network-attached FPGAs. And these are just examples of how people utilize FPGAs in the context of distributed applications. However, it is still very challenging of designing distributed applications with FPGAs, partly due to the tool change and infrastructure lagging behind and does not provide equivalent that you can easily get in the software world. And one very important factor is the lack of high-level communication abstractions in the hardware. Collectives, for example, broadcast, scatter, gather, and reduce are really the cornerstone of distributed application nowadays, especially for distributed machine learning inference and training. And we have already seen the advances of collective libraries for accelerators, for example, Nico and Rico for GPUs. However, there's not enough support for collective abstractions on FPGAs. Therefore, for distributed application on FPGAs, many times it has to rely on the CPU to perform the networking task, and this incurs a lot of efficiency in terms of data movement and the control overhead. So we propose Echo Plus, which is an adaptive collective communication library in hardware. And the overall goal here is that we want to provide a flexible, portable, and high-performance collective abstraction that can be accommodated for different applications. And to achieve this goal, Echo Plus actually builds on top of various different abstractions in the hardware. In the central part is the collective offload engine, the CCLO. It is flexible, and here flexible means that it is it can support a wide range of collectives at the runtime without the need to recompile the hardware. And also it is high performance, saturating 100 gigabit line rate and achieves a very low latency. And one layer below, we have various transport layer stacks. For instance, Echo Plus can support different kind of transport layer protocols, including EasyNet TCP and the Coyote RDMA. And both are hardware networking stacks developed in our group, ETH Systems Group. And also Echo Plus can be extended to support other type of transport layer protocols as well. Also, Echo Plus can support different FPGA shells and FPGA board. For instance, we already support a commodity platform, AMD Vitis, which provides a partition memory model. And also we support Coyote, which is an open source infrastructure developed in our group, and it provides a shared virtual memory across the CPU and the FPGA. So with these abstractions in the hardware, we can already utilize it to build distributed applications. And on one hand, Echo Plus can be used as a smart NIC to offload the networking tasks from the CPU. And on the other hand, it can also be used as orchestrator and enabler for distributed applications that runs on top of a fleet of accelerators. And now let me introduce you the key design principle of the collective offload engine. So the overall target here is that we want to have a collective offload engine in hardware. It should be high performance and also at the same time flexible to support different collectives and different algorithms. One approach that you can do it is a hardware solution where you implement all the collectives in a digital logic. And in this example, you have different modules for different collectives, and then you can employ some on-chip routing resources to route the user request to different modules. However, this approach will provide you with a very low scalability because each modules will consume hardware resources and it will soon run out of the on-chip resources. And this will provide you very low flexibility because every time you want to modify or update the collective implementation, you need to recompile the hardware and it will take hours. On the other hand, you can adopt a software approach where you can synthesize embedded microcontrollers on the accelerator fabric, and then you can implement the collectives in the microcontroller firmware. And in this way, you can have higher flexibility. However, because the microcontroller executes sequential code, and many times on the FPGA, it is operated at a lower frequency, so in the end, you might be bottlenecked by the microcontrollers. Therefore, we adopt a hybrid approach where we have a flexible control plane centered around the microcontroller and also a high-performance data plane implemented in digital logic. So here, this is the overall architecture of the collective offload engine. You can see there is a clear separation of the control and the data plane. And only the message header is routed into the control plane while the payload is processed at the data plane. In the central part of the control plane resides a microcontroller, and we further try to minimize the code footprint of the microcontroller. For instance, we designed dedicated data movement processor which handles the memory accesses for the microcontroller such that the microcontroller will not be stalled because of waiting for the data. And also, we designed a receiving buffer manager which automatically reassemble the messages from packets and perform other tasks such as tag matching. So with this dedicated logic in the control plane, the microcontroller can focus on the implementation of collectives and use some high-level data movement primitives. And these data movement primitives allows you to describe when do you want to move data, how do you want to move the data, and the actual execution of the data movement primitives will be handled by the underlying hardware logic. So in the end, we have a very flexible design that can support different algorithms at a runtime, and we can support both eager rendezvous protocols, and we can easily update the collective implementations by updating the firmware without re-synthesizing the whole hardware. In the data plane, we employ multiple independent hardware modules, and it operates at a very wide data path, which is 512-bit, and this allows us to perform parallel arithmetic processing, and this is the key to achieve high-throughput systems. And now let me introduce you how Echo Plus can be used in different scenarios. First, let's talk about using it for distributed accelerators, and in this case, the FPGAs are viewed as the first-class computing resources, and the application is spread across multiple nodes. And here, the application will read data from the FPGA memory, do some computation, and afterwards, it will send the data to the collective offload engine and invoke the collective offload engine. In this case, streaming is a very important property because it allows the application to push the data into some dedicated channel directly to the collective engine without requiring temporary buffering in the memory space. So Echo Plus provides this streaming API that is well integrated into some high-level synthesis system and allows the hardware programmer to overlap the computation and the communication. On the other hand, Echo Plus can be used as a smart NIC, and in this case, the application runs on top of the CPU, and it will do some computation and store the data to be transmitted back into some memory space, and afterwards, it will invoke the underlying collective engine. The collective engine will read the memory buffer and send it through the network, and of course, you can also embed other type of acceleration or data transform along the network data path. So in this case, both the CPU and the FPGA needs to access the same memory location. Therefore, a shared virtual memory is very beneficial, and this is what's being provided by Coyote. And to accommodate this workload, we propose a message passing API that is essentially very similar to what is being provided by existing collective libraries and other MPI implementations. And this allows existing software application to easily use Echo Plus as the communication backend. And now let's take a look on the evaluation. We will focus on Echo Plus with RDMA, but it also supports other type of communication protocols. We focus on both scenarios, distributed accelerator scenario and SmartNIC scenario. However, due to the constraint of time, we will only talk about the first case. And we use F2F, means FPGA-to-FPGA here. So here you can see the green boxes on the FPGA, and this means the data, because the data resides on the FPGA. And now you can either use Echo Plus to move the data directly between accelerators, indicated by the red array. And also you can either use a CPU as an intermediary to move the data, and this is indicated by the blue array. And let's take a look on the send and receive throughput. Here we demonstrate a different configuration of Echo Plus in either distributed accelerator scenario and SmartNIC scenario, and also we compare it with OpenMPI running on top of the commodity NIC. So what we can observe here is that our solution can easily saturate 100 gigabits line rate, and it is very similar to the performance provided by other type of collective libraries. And now let's take a look on the collective performance with RDMA. And here we demonstrate several collective implementations, and they all use the same piece of the hardware, and it can be extended to support other type of collective as well. And here we focus on the latency. This is a number across 8 different nodes. And the blue line indicates the Echo Plus solution, while the red line indicates the OpenMPI baseline. Generally speaking, we can see that we achieve a lower latency. And also in the figure here, we demonstrate that we can achieve very high flexibility. In the reduced plot, we can see a bump in the blue curve, and this is the place where you have the collective algorithm change. And also in the broadcast figure, you can see the effect of tuning the message synchronization protocol. And Echo Plus allows you to tune these parameters at runtime. Now, with the infrastructure we have been built, let's take a look how we can distribute an application. And our use case is a deep learning recommendation model. The deep learning recommendation model generally takes 2 major components. One is a very memory-intensive embedding lookup, because during the embedding lookup, it will incur a lot of random memory accesses. And also another one is the compute-intensive fully connected layer inference. In our prior work, we have already looked into a single FPGA acceleration where we utilize the high bandwidth memory and the on-chip compute resources to accelerate this workload. And in our case, we further extend on our prior work and see how we can distribute a larger model that requires partitioning across multiple nodes. And this is one example of how you can partition a larger recommendation model. And this is the Alibaba recommendation model. We partition it across 10 different nodes. Here, the embedding layer are partitioned across several different nodes, and each node will perform the concurrent embedding lookup and do some partial computation of the first layer. And these partial results and the partial vector will be forwarded to the next group of accelerator in a streaming fashion. And the second group of accelerator will perform the rest of the computation, and the result will be aggregated through a reduce operation. And afterwards, the second layer and the third layer will be computed in a pipeline fashion. Let's take a look on the evaluation. Here we demonstrate a latency and the throughput comparing with the CPU baselines. We could observe that in terms of latency, the FPGA solution achieves more than 2 orders of magnitude lower latency. And also in terms of throughput, we achieve more than an order of magnitude higher throughput. And in our paper, we also have other examples demonstrating how to use our infrastructure in the form of a SmartNIC, and please check it out. And with this, I would like to conclude, and all our projects are open source, and it is ready to download in the GitHub repository. Thank you.